morning, everybody, or afternoon or evening, depending on where you're at. So hopefully you've gotten this link by now. The instructions are pretty simple. You just click this link, but we'll have to upload the data separately. So this requires you to create an account and so on, but it's all free. Let me go ahead and open this up. Okay, the first thing you'll need to do is make sure the runtime has a GPU on it. So you can change the runtime by going up here, change runtime type, and make sure that GPU is selected. Okay, a brief introduction about what we'll talk about and what we sort of won't focus on. So this is about gaining an intuition for how to convert your tabular structured data into graph structured data. We will work through this little fraud detection example. It uses this open source data set, but I want to emphasize the focus will be on preparing the data and not necessarily on the graph modeling piece. I did build a couple models, and feel free to run them and play with them, but we won't talk a lot about the details here. And if you do want to learn about modeling, I just started this free course, The Basics of Graph Neural Networks. It's a lot of my YouTube content repackaged, but there's also some quizzes and exercises and stuff. But you could take that in a few hours and get up to speed with the basics on the modeling. And then if you want to go deeper, there's these the Introduction to Graph Neural Networks course that will be opening up here pretty soon for the next cohort. Okay, so the first resource I want to point out is from Neo4j. They're a graph database vendor, and they have this nice guide that describes, if you're an enterprise, how do you convert your relational databases into a graph database? But a lot of these principles can be applied for these tasks of graph modeling as well. And it's a long article, and it goes into great detail. Here's an image from it. But if I had to summarize it in just a couple bullet points, the idea here is that you have, let's say, a table of employees or people, and then you have a different table that describes your various departments. Well, each row in each table will be a node. So employee Alice will be a node, and her node type will be indicated by this table. So since this is the person table and she's a row in the person table, she will be a person node. And likewise, in the department table, you'll have a node for each department, and the type of that node will be a department. And then there's usually something like a join key that relates Alice and indicates some ID or something of which department she belongs to. And if you were writing a SQL query, you would do something like you would join on department ID between these two tables, and then you could pull in the department information for Alice. In a graph representation, those join keys will basically be our edges. So the ID of the department will point to the actual department she belongs to, and that allows us to draw these various edges. And then the columns in these various tables, whether it's the people properties for Alice, or the department properties, maybe it's location or business function or something, those could be included as node properties. Okay, so that's relational databases, but how do you do this for a tabular data set, like in a Kaggle competition, for example, or maybe your task at work? First of all, I want to make it clear that just because you can represent your data as a graph doesn't mean you should. It's not obvious that graph and graph-based methods are going to be better than the tabular-based methods. So you really don't know until you start trying things. And kind of the key question you have to ask yourself is, are there relationships between your data points that are helpful in solving the task at hand? And that's not always clear, but some exploratory data analysis might be helpful. And a lot of the times you're just going to have to try it out to see what happens. But there's more than one way to do it, as we'll see. And it takes a little bit of creativity in some cases. But with all of those caveats, let me kind of tell you my high-level approach of how I start thinking about this. The first thing I usually do is look at the number of unique values in each column because typically your entities that are sort of identifying or are meant to identify individual entities have very high cardinality or many unique values. So these will be things like the user ID or the credit card number, the transaction ID or the movie, if it's like a movie recommendation use case. So those are good candidates for your nodes. They represent these kind of individual entities. And then there's often additional columns that are properties that describe those entities. So for example, you might have the age of the user or the country of the credit card or the title or genre of the movie. And those are good candidates for node properties. Edges are many times expressed as verbs that kind of relate the entities together. And these will not necessarily be a column in your data set, but is more your understanding of how the pieces of the data fit together. For example, you might have a row that indicates the user, the movie, and the rating that they gave. Well, the user and movie might be your nodes, and you sort of understand semantically from the data set that the user is rating the movie. And you can express that as a verb, as the user rates the movie. And that's an indication that that might be a good edge, because you need some way to kind of link your nodes together. Another example, if you have users and transactions, might be user buys product, if you have user nodes and product nodes. Now, you're not going to have a column that says buys, but you're going to understand from the nature of the task that this user is buying a product, and that's what's relating these things. Or maybe you have the person who directed a movie and can have a directed by. So there's lots of different ways you can relate these things, and there's several different options, and that's something you'll have to play with. And then sometimes there's covariates that describe these actions or relationships and are candidates for properties on the edge. For example, the actual rating that a user gives to a movie might be an edge property, or the purchase amount or count. There's considerable ambiguity when you're trying to decide whether a column should be a node or a node property. For example, the country of a user might be a good node property if you want to one-hot encode that or some other technique. But it could also be a good node. And whether it's a good choice or not is related to both the task and which algorithms you plan to use. Because some algorithms benefit from having lots of connections, and others benefit from more sparse connections. So there's this kind of interrelatedness between downstream choices in your graph structure. So there's no single answer, and you're going to have to experiment. So let me pause here. Are there any questions about high level how to approach structuring your tabular data as a graph? Sorry, let me read these questions real quick. The first one is, what are you looking for? More relationships or more nodes as a preferable choice? I would say in general, you want not that many edge types, because the reason I say that is it's been a challenge for the field to come up with effective heterogeneous models that really take advantage of diverse edge types. There has been progress there, but oftentimes ignoring the edge type and simply treating it as a homogeneous graph works reasonably well. But there are specialized techniques that could take advantage of it. So yes, you can use different edge types. That would be called a heterogeneous graph, and that's what we're going to do in this example. Okay, how do you tackle capturing relationships between nodes that wouldn't typically have one? For example, a stock in the stock market. Yeah, that's a good question. So it could be that, first of all, this could be one of those cases where it doesn't make sense to have a graph, and that's always a possibility. But you can also come up with other approaches that are more empirical. So for example, you can get a similarity metric between two stocks, and then say, if that similarity metric is above some threshold, then I'll create an edge. So similarity might be, for example, the correlation in values over some time period. And if there's a high correlation between the prices of those two stocks, then you draw an edge between them. I've done similar things with, for example, in a fraud detection use case, I had embeddings for email addresses, because what we would see is the fraudsters would have a base email address, and then they would add this kind of small change to the end, like a number or something. And then they would create a bunch of accounts with these small changes. So I couldn't relate them exactly because of the email address, because there were these changes, but they were highly similar. And I trained a deep learning model that basically could capture that similarity. And then when I took the dot product of those vectors, the ones that were very similar had a high value. So then I could draw edges by just getting a threshold on that. I'd say, okay, if the similarity is greater than 0.95, then draw an edge between them. Okay, can you take pairwise distances between the rows? Oh. Yeah, so what would be a reason to go with node instead of attribute transforming a column? For example, with label propagation, I found that you want information to be able to spread far. And if you have very sparse connections, you may not have a connection with a training label, because in label propagation, you're basically taking a small set of training labels and spreading them through the edges in the graph and smoothing it to get predictions. But that requires you to have connections with training samples. And if you don't, then you're never going to get a meaningful update. So in that case, it's beneficial to have lots of edges. And in that particular example, I would err on the side of turning a reasonably high cardinality attribute into a node, because that's another information pathway to spread the labels. On the other hand, with something like a graph neural network, that could be problematic, because whenever you go 2 hops away to aggregate information, if you have something that's connecting you to 10,000 other nodes, then you're going to need those 10,000 nodes to make a single prediction for your target. And that can be wasteful. So it depends on the algorithm and the downstream application, I would say. Okay, moving on. So again, you will have to download this data set. Let me upload it real quick. Okay, so now the data is uploaded here. It will warn you that Google did not create this notebook. Okay, first thing we need to do is install DGL. And that depends on the version here of CUDA and so on. And this might be different for you depending on which GPU you get. But this should be pretty straightforward. But unfortunately, it resets the environment every time you open the notebook. So you'll have to continually do this and re-upload the data. And you'll also want to check that this device here says CUDA, because if it says CPU, then you haven't allocated the GPU. You'll need to reset that. Okay, so this just extracts the data from the tarball. And here are the variable definitions for this data set. We basically have transaction IDs, something called batch ID, an account ID, subscription ID, customer ID. So anytime you see something that says ID, that should automatically tell your brain this would probably make a good node. And there are reasons why not all of them will make a good node, and we'll talk about that. But whenever you see an ID, that typically means it's highly specific. And that means if you have a connection with that thing, it's probably going to give you useful information that isn't something that's incredibly general and true for many, many nodes. We also have currency code, country code, provider ID, product ID. So I would also, before looking at the data, consider provider ID and product ID as possible nodes. And then there's like the value of the transaction. One of them is positive or negative. Oh yeah, positive for debits and negative for credit. And then value is basically the absolute value of that. We have a time pricing strategy, and then the fraud label. Okay, so if we do a quick exploratory data analysis, see we have 140,000 transactions. I've concatenated the training and test data sets and then created these indicators so that we can slice it by that. And the first thing I'm going to do is group by the data set and look at the number of unique of each of these items. So we see that for training, the transaction ID, there's 95,000 something unique, which matches just the number of training rows. And likewise for test, 45,000, 45,000. So transaction ID is unique across every row, meaning you don't see the same transaction ID twice. Batch ID is very similar to that. So I'm actually going to ignore batch ID since it won't connect more than a couple transaction IDs. In the future, maybe I would try to add that in and see if it gave very specific information, but as a first pass, I'm going to ignore that because it's basically a duplicate of transaction ID. And I should point out, the transactions are the things we want to make a decision for. And since we're going to make these nodes, that puts us in the world of a node classification task. So for every transaction ID node, we're going to make a fraud prediction. And those are the things we have labels for. So that's another thing to start with is, what are my labels for? Are they for an entity? Are they for a relationship? And that helps you cast this as either a node classification problem or a link prediction problem or so on, edge classification, whatever the case may be. Okay, with account ID, subscription ID, customer ID, we see that there's thousands of unique. And furthermore, it's many less than the transactions. So that tells me that, for example, an account ID is going to have maybe 10 or 100 transactions that are associated with it. And that's a good thing because that means for any given transaction ID, if I go to its account and then look at the other transactions, that those are closely related transactions that will likely give me information relevant to fraud. Because if some of those transactions are fraud, I'm assuming that that's going to increase the likelihood that the current transaction is fraud. And similar is true for subscription and customer ID. There's around, there's something in the order of thousands of them. Currency code, there's only one, so that's not going to be useful at all. Same with country code. Provider ID, which I considered as potentially being a node because just it says ID in it. I could imagine there being many providers. In this case, there's only 6 providers. That's not going to make a good node because that's going to connect every node to approximately 1/6 of your graph. And you don't want to use 1/6 of your graph to make a prediction for a single node every time. Likewise for product ID, there's only 20 something of them. These are going to be a better property of your transaction than they will be independent nodes. There's just too many connections that would result from that. Same with product, category, channel ID, all of these things, I'm going to basically one-hot encode as a property of my transaction. If some of these described a customer or a subscription, then I would make it potentially a node property of those nodes. But first of all, I don't really understand this data because they don't provide much guidance, but I'm assuming these are properties of the transaction. What this also implies is that we don't have features for these other nodes, and we'll have to handle that some way, which we'll get to in a minute. We have a reasonable variety of amounts and values, but these are numerical values. So we expect these to have a lot of unique. That does not make them good candidates for nodes. These are numeric. So these will also be properties of our transactions. Numeric data is different. It rarely makes sense to represent a numerical value as a node. You would need to, of course, bucket it or something like that. And maybe there are use cases where that makes sense, but here I don't think it does. We're going to ignore time. You could obviously split this into hours or days or something like that and make it a property, but we're going to ignore it. Pricing strategy is like these other, there's just a handful. And then the label, of course, that we're going to train on. So in summary, transaction ID is unique, and that's what we're going to make predictions at. Batch ID is also almost as unique as transaction ID, and we're going to ignore it. Account ID, subscription ID, and customer ID have thousands of unique and connect the transactions. So we're going to consider these as nodes. We're going to one-hot encode these categoricals as properties of our nodes. And then for the numeric, we will use those as properties as well. Okay. So I did a little bit more analysis here. This just shows that the average fraud rate in the training set is 0.2%. So that's quite a low fraud rate. Means we have a pretty significant imbalance here. And I was curious about how accounts and customers relate. And if you take the average number of customers associated with an account, you see it's around 3. And if you take the average number of accounts associated with the customer, it's about 2. So there seems to be a many-to-many relationship between accounts and customers. It's not that one account can have multiple customers, but not the other way. It's a many-to-many relationship. So that complicates things a little bit since we don't really understand this data. It was just given to us as a CSV file. In a real life problem, you would have a much deeper understanding of the problem space. Okay, so here's what the raw data looks like. Our basic strategy is that if we make, let's say, a node out of this transaction and a node out of this account, that since they occur in the same row, we know they have a relationship. So we know that this transaction ID is associated with this account ID and this subscription ID and this customer ID. So if we had nodes for each of these 4 elements, we could construct edges among them in any way that we want. We can put a transaction to account, transaction to subscription, transaction to customer, but we can also put an account to subscription and a subscription to customer and any combination of these that we desire. The first thing I do is I associate an integer ID with each of the unique values here. And then I have a map that basically goes from this string to the index, and that will be the node ID. So each node type will have an ID that's associated with essentially the row in the matrix. And I want to be able to keep track of that. So that's what these various dictionaries are for. And then we can put them back into our data frame by using them to look up from the raw value to the integer name. I just extract the labels here. In this case, I restricted to these node IDs. I like to start as simple as possible, but I also wanted this to be a heterogeneous graph situation. So that's why I used sort of the minimum of 3 node types, which will give me 2 different relationship types. Okay, so this is essentially what the data looks like with the node IDs instead of the strings. When I add up the number of unique nodes, I get 150,000. So now we essentially have all of our nodes. We have transaction node 0, transaction node 1, all the way up. We'll have similar IDs for subscriptions and accounts. Now we need to construct the edges. And again, this is going to be the co-occurrence in a row will make an edge. So we'll have a transaction connected to a subscription. And then the edge type we're going to assign is basically just the concatenation of the types. So we have transaction index connected to subscription index, and the edge type we're going to call transaction index hyphen subscription index. And then we're going to reverse that relationship so that there's an edge pointed in both directions. So this is identical to the thing above it, except for this has come over here and that has come over here. And then likewise, we flip this relationship around. And we do that for all the combinations. And again, if this were a real life problem and I understood the data, I would probably not do this. But since I don't understand the data and I have no reason to eliminate one type of edge over the other, I'm just going to include them all. So I have transactions connected to subscriptions, transactions connected to accounts, and subscriptions connected to accounts. And basically what we do here is we select the columns here. So for example, transaction and subscription, and then we remove the duplicates and we say this column is the source and this column is the destination. And we record that. So here we're slicing with the two types, dropping the duplicates, and then we say, okay, this is the source, this is the destination. And then we add both directions because we want the reverse edges. And now we have a dictionary that basically maps this key to this tuple of tensors, the source and destination. And that's the data structure you need to create this DGL graph. So it says for each type, each relation type, what are the source and destination IDs? And with that, we now have our heterogeneous graph, HG. They have this in types property that tell you the name of the node types, which they extract from the keys of this thing. And we see we have an account index, a subscription index, a transaction index. So now I want to associate my labels that I have with my nodes in my heterogeneous graph structure. And the way this structure works is that you essentially have a dictionary where the first key is the name of the feature, and then that maps to another dictionary, which says what the values are for each node type. So we have labels for our transaction index. That's the ground truth labels given to us in our transaction data set. But we don't have labels for the accounts and the subscriptions. Because remember, these occur potentially tens or hundreds of times each. And our labels are at the transaction. So we don't have a label for an account or for a subscription. So what we're going to do in this case is just fill it in with the dummy value, which is equal to our baseline fraud rate. We're only going to use these labels when we're doing label propagation. So when we're training a GNN, these labels are never going to be used. We're only going to use the transaction index labels, our actual fraud result, and that will update the parameters of everything. But for label propagation, where we are sending label information from each of our nodes, we need some value here. And the best we can do is give it some dummy value. So again, for transaction index, we use our ground truth labels given to us, and for everything else, we just fill in the dummy value. If we now look at our heterogeneous graph, we see we have about 4,800 accounts, 4,800 subscriptions, 140,000 transactions. And then our label information, if we look at the node data, we have a dictionary that says label, and then these are the tensors. So it's all the same 0, 0, 2 for accounts and subscriptions, since those are the dummy values. And then our transactions have the actual labels given to us in our CSV file. Okay, now let's take a quick look at our graph. One thing I did here was created a visualization where transaction nodes are circles account nodes are triangles, and subscription nodes are squares. And then for the circles where we actually have ground truth data for the label, if it's legitimate, I color it blue. If it's fraud, I color it red. And if we don't have a label, like in the test set, we color it black. I can now create a data loader in DGL that kind of goes over this, the 2-hop neighborhood, or however many I want. In this case, I chose 2, the 2-hop neighborhood of a target node, and plot the visualization. So I start by looking at just the legitimate cases, where the label is given to be as 0. And if we take a look at this, let's say this is our transaction node, it's connecting to a square and a triangle. These are the accounts and subscriptions. And then each of those are connected to transactions. And we see that all of them are blue. That in the 2-hop neighborhood of a random legitimate transaction, all of the other transactions that connect to those subscriptions and accounts are also legitimate. And there's a variety of structures here. Like this one is pretty sparse. There's not many connections. And here there's quite a few. And I've limited it to a maximum of 10 neighbors so that it doesn't explode. But I think the first thing we've learned is that if we crawl the neighborhood of a legitimate transaction, we see lots of other legitimate transactions. Now, the next question is, of course, what happens for fraud? And it turns out that in the neighborhood of fraud, there are other fraud. And that's great news for us, because our whole hope here is that by relating one transaction to other transactions associated with the same account and subscription, that there will be useful information that helps us make a prediction. And the fact that fraud tends to connect to other fraud is an indication that this graph structure is useful, and therefore will benefit by using it. Yeah, you rarely see a fraud not connected to other fraud, but because the number of transactions is so imbalanced, we also expect to see many legitimate transactions in the neighborhood as well. It's not all fraud, it's a mix. Okay, so that's kind of our first signal that we're on the right path here. I go ahead and have a function that calculates some statistics here about the number of the neighborhood size and the amount of fraud in this 2-hop neighborhood. And when I group by the ground truth label, we see that the neighborhood sizes for legitimate on average are much larger. So we have like 30,000 here compared to 800 in the case of fraud. So fraud neighborhoods seem to be smaller. If you look at the fraud rate of the labels, in the legitimate case, you have less than, you have around 0.1%. And in the case of fraud, you have like 25%. So obviously a huge change here. That's another good sign, because at the end of the day, we're looking for signals that can help us determine whether something is legitimate or fraud. So if we can look in the neighborhood and observe the labels, and that has a huge difference between whether the neighborhood is in a fraud or legitimate case, that means we have a signal for our model that it can use to predict. If we visualize this, this is the distribution of the fraud rate in the 2-hop neighborhoods. We see that in the case of fraud, it kind of runs the whole gamut. But in the case of legitimate, it's basically totally at very low fraud rate. Neighborhood size is a little bit more interesting. We see that this is a log of number of nodes, that in the case of legitimate, there's this really strong, heavy tail where several nodes have 10 to the 5 neighborhood sizes. And we don't see much of that in the case of fraud. But then if that's not the case, then we see reasonable overlap in the rest of the distribution. So in other words, if you're connected to many nodes, you're probably legitimate. But other than that, it's probably difficult to tell. Okay, node features. So again, we decided to use these as properties of our nodes because they're relatively low cardinality. And it would not make sense in most cases to make these into nodes because it would connect huge portions of the graph. We're going to one-hot encode these, and again, these numeric values we'll handle separately. So here, we just do one-hot encoding. And then for the amount, remember that it's negative in one case and positive in another case. So I just create a binary indicator for the amount of whether it's positive or negative, and then do a log transformation of the value, which is a standard thing to do for dollar amounts because the variance can be so large. And that's it. These are the node features for all the transaction nodes. So they will be mostly zeros because it's a lot of one-hot encoding. And then the last two numbers will be these float values. Okay, on to the modeling piece. So I like to start as simple as possible. And I have a couple convenience functions for plotting, but I'm going to start by just doing a logistic regression and random forest on the raw features and ignore all the graph structure and see what we get here. So I fit my logistic regression, and I'm just, again, using these features that we have, which are the one-hot encoding of the categories and the amounts and so on. So no graph information. I look at the coefficients, which can be a sign of the importance of the various features. We see one of them stands out. I then take the correlation of the value of the column in our input data with the target and plot that, and we see that the one with the very large coefficient is also the one with the highest correlation. Not surprisingly, this is our one and only numeric value. So you're not going to get much correlation probably out of a binary variable like most of our columns. So it's not surprising that this one has a higher correlation. However, it does seem to be highly predictive of fraud. And if we look at this one feature, which is the log of the amount or the log of the value of the transaction, and color code by fraud or not fraud, we see that the fraud cases tend to have a significantly larger value than the legitimate. However, this has been normalized so that the population sizes are about the same. You know, the area under the boxes is equal across these two populations. But in practice, we know that there's many, many more legitimate transactions than fraud. So if we remove this normalization and look at the raw counts, we see that all of the fraud is here, but there's so little of it that it's a very small magnitude. And it could be that there's just as many legitimate in this range as there are fraud, only because the size of the legitimate population is so much larger. So what looks like a really easy problem here might actually be hard because of the class imbalance. Another one with reasonably high correlation is this one-hot encoding of the product ID. In particular, product ID 15 seems to be predictive of fraud. There's a substantial different distribution here. Okay. I then fit a random forest model just to see if there are any kind of nonlinear effects in the input space or outliers or something that are causing problems. These are the results. So we get very high performance right out of the gate. And I would be thrilled in most real world settings to get a model this good. So it's going to be hard to beat this. But also note that on the ROC, I'm only going out to 5% here. That the full ROC curve will go, of course, out to 100% false positive rate. So this thing is very much like up and to the left. It's almost a perfect model. So that tells me that the features are highly predictive of the target. Usually the precision recall is going to be a probably more useful metric here. The problem is that it's biased by the fraud rate, which is either a feature or a bug, depending on what you're trying to do. So here we see that there's quite a bit of difference between the random forest and the logistic regression models. I fit one with balanced, basically applying weights in the loss function to balance the classes, and one without that. But we see that the performance looks much different in this view, that the random forest is doing significantly better. We have our baseline models. Now we can deal, oh, there's one other thing I did. I added a graph derived feature and then included it in logistic regression to see if that added lift. Because if you can't conceive of a simple graph-based feature that gives you lift and verify that, then that's probably a bad sign. So in this case, I just used the same statistics before, where I looked at the fraud rate in the 2-hop neighborhood, and I included that as just a feature and fit another logistic regression. So that's this red one here. If we look at the PR curve, we see that it does have benefit, particularly in this high precision, low recall area. So that's another reasonably good sign, although I would have liked to have seen an improvement across this full operating range. Okay, next we move to label propagation. I actually provided 2 implementations here for those that are trying to learn DGL. I have basically label propagation using their message passing APIs. And then I also do it with raw matrix multiplication that you would typically see with sparse matrices. But basically the process here is that you get your neighbors' labels in a message passing scheme by multiplying with the adjacency matrix, which is weighted. So this will collect all the neighbors and apply different weights based on how many connections they have and give you an update. And then you balance that update with the original ground truth that you have, so that basically the training labels don't get squashed immediately. So you're continually pumping in the training label information while balancing that with what your neighbors are telling you. And you iterate this over and over and over until it converges. So first, label propagation is typically for homogeneous graphs, not heterogeneous. So we go ahead and convert our graph to a homogeneous one. And the thing we're going to be sending around in the messages are the labels. And remember that for those subscriptions and accounts and so on, we just gave them dummy labels. So they will have like a baseline rate of 0.002, and they'll be sending that along their edges. But then the next step, they will collect the ground truth labels from all the transactions and use that to update their own label. So then in the next iteration, they send that out. We go ahead and apply that. I plot it for the various iterations. We see that it very quickly converges to reasonable performance. Now keep in mind that none of the raw features are used here. This is only the graph structure. So this is only the connections between the transactions, the subscriptions, and the accounts with no feature information. And we see that we get a pretty good model. Not as good as using the features, but it's still over 0.9 AUC. However, in this view, we see a substantial difference. It struggles with recall and this high precision, and you have to get pretty low precision to get most of the capture here. Okay, so on to the GNNs. Again, I'm not going to go into the details here, but you can play around with this. I have various functions for plotting and doing the training and inference. The basic architecture here is going to be a relational GCN. So it's basically neighborhood averaging, but you'll have a dedicated projection matrix for each relation type. So in other words, a transaction will aggregate the subscription information, and then it will aggregate the account information, and then combine those together. But the aggregation is at the specific relation type level first, And then at the end, it combines all of the relation type information together. So my overall architecture is to have kind of multiple RGCN layers with batch normalization. And then the output of that, I concatenate with the original raw features and apply a regular linear layer. So I concatenate the embeddings coming out of the GNN with the raw features and then pass that through a logistic regression, in other words. So here we pass in the graph, which are these blocks, and iterate through them while applying the RGCN layer, extract the raw features, and then concatenate, pass through the output layer. The other trick I apply is label smoothing, and this is because in fraud data sets, there's often incorrect labels. And if your model turns out to be correct, and for example, identifying something as fraud with very high confidence, but your labels are wrong, let's say it's a 0, then that can lead to a really large error because the cross entropy goes to like infinity when your model is highly confident and is wrong. And then that can lead to a very large gradient, which throws your model off in training. And if you smooth these labels, then it reduces the impact of these mislabeled outliers. So I applied that. Okay, the question of, there were two questions. First is, what do we use for label or features for our other nodes? Because we have features for our transaction nodes, which are the amount and the product category and so on, but we don't have features for the account or subscription nodes. There's several options of things you could do. In this case, we're just going to use random numbers. And I don't want to go in too deep as to why this works, but one thing that you can think about is that this assigns kind of a unique ID to each one. And by aggregating all of your neighbors, that if 2 transactions have the same connections, that when they average these random numbers, they will end up with the same answer. And the same answer means they'll have similar embeddings. So even though the values are random, if 2 things are connected to a bunch of the same stuff, when they average those random values, they're going to get the same answer. And that means they'll be close together in the embedding space, which is what we want for things that are connected to a lot of the same stuff. So that's one explanation. I talk about this a lot more in the course if you want to go deeper. Another thing you could do is just map it with zeros, because we don't really care what the value is, because after the first message passing step, it's going to combine its neighbor's information, and that will be its new representation. So if it's passing zeros around, it doesn't really matter, because what we actually care about is the output after the next step. So in other words, our subscription, it'll start with zeros, but after the first GNN layer, it's going to pull in the features of all the transactions it's connected to, apply the neural network, and now it will have a new representation that's not all zeros. And then that will be used for the downstream steps. Another common technique is to initialize these with random values, but they're learnable parameters. And then you optimize these parameters in the training process. This can be really effective, but it also has challenges, because if your test node, for example, isn't connected to any of the training nodes, then it will never receive a training signal that updates the parameters in the training process, and the model will perform poorly for that node. So you need to make sure that if you do the learnable parameters approach, that your test nodes are well connected with your training nodes. Oh, the other thing you can do is calculate features based on the graph, like structural features. And I do that a little bit here with the degree. So I create a feature for all of the nodes based on how many connections it has. And things like that, counting triangles, for example, or running some kind of WL test that gets these representations that describe the structure in the local neighborhood is another way you can generate features for otherwise featureless nodes. Okay, so here I just do the label smoothing loss function. I tried to tune this a little bit, but I think there's actually a bug somewhere because this model, I could never get to converge quite right, and it seemed to be sensitive to the random seed. So I don't know if there's a problem with the data structure itself or in the model that I haven't yet found. But you can play with this and see what you get. But ultimately, it does better than label propagation, but it's not matching the logistic regression, which is what's making me suspicious because the raw features are ultimately being concatenated and tossed into a logistic regression. So it should never be worse than that. But in any case, we see that it's doing better than label propagation by leveraging the feature information. Okay, so let me go back to the questions. Okay, how can I ensure that train and test nodes are connected? You can do something similar to what I did here, where I was calculating statistics around like the labels. So if you have the adjacency matrix, that tells you which nodes are connected to which nodes, which basically in the one-hop neighborhood. However, if you square the adjacency matrix and look at the values, let's say you have row I and column J, and let's say that the number in there is 3 after you've squared the adjacency matrix. And what that tells you is there are 3 paths of length 2 between nodes I and J. You know it's length 2 because you took the second power of the adjacency matrix, and you know there are 3 paths because the number is 3. So if you had, let's say, a 4-layer GNN, then you could take the 4th root, or not the 4th root, the 4th power of the adjacency matrix, and then that would tell you how many paths of length 4 exist between all of the nodes. So you know which ones are the train nodes, you know which ones are the test nodes. So you could look how many paths of length 4 exist between my train nodes and my test nodes. And that would tell you basically, you could isolate which test nodes have no connections with the train nodes. And if I were doing this properly, I would say, I would train my model, I would look at the performance on the test set, and then I would break it down by how many connections it shares with the training nodes and see if my model performs much better if there are lots of connections and much worse if there are very few connections, something like that. And that would give me a hint of if I need to potentially modify my graph structure or approach. How did you do the train test split? Yeah, in this case, I just randomly split the training data. I did not consider the graph structure when doing it. I think if I were doing this for real, I would consider time, because typically time is very important in fraud detection cases. And I would suspect that the connections are also time sensitive, so that things that happened long ago are more likely to connect to one another than things that are new are connecting to old. So time is usually important both in terms of your model's ability to generalize and in describing the graph structure. One thing I might consider to take advantage of time is, and this would be a totally different way of representing the data as a graph, and that would be something like only have transaction nodes and use different edge types based on shared account ID or shared subscription or shared, what was the other one? Account subscription and whatever the other one was. So in that case, I would have only one node type, but I would have multiple relation types. And the problem with that is that, let's say you have 10 transactions connected to the same subscription, and you want to have an edge that connects the transactions that share a subscription. Well, then you have basically a very densely connected cluster of 10, because every transaction would have to have an edge to every other transaction. So you'd have like 100 edges in this thing. And the way that you could reduce the number of edges is say, I'm going to only connect to the one that's most recent in time and is before me. So then instead of having a cluster of 10 transactions that are all connected to one another, you would have 10 transactions where each one is connected to the most recent transaction before it. So you'd have kind of a line. And in that way, you could actually use the label information, because you would be ensured that you're not leaking future label data, because you're only allowing messages to pass from something older to something newer. So that would be an alternative way that both leverages time and directly connects transactions to transactions, instead of having to go through these intermediary nodes of accounts and subscriptions. Because since we did it that way, we have to worry about generating features for featureless nodes. But if we did it in this other way I'm describing, with only transaction nodes, you don't have to worry about that, because every node is a transaction and we have features for every node. So that's probably the next step that I would do, of how do I test a different approach to structuring my data as a graph that might learn from some of these lessons, because I think this featureless nodes problem and having to add in random values is probably going to hurt performance. Is the time obviously encoded in connectivity or only node features? I haven't explored that with this data set, but I think it's likely that time is relevant to the connectivity as well. Like I suspect, for example, the batch ID is all of the transactions within a narrow time window, maybe is what that means. I haven't dug into it yet. And in that case, transactions in the same batch might have happened within a very short time window of one another. So you could imagine establishing a new edge that basically relates transactions in time. Or even if batch ID does not mean that, you do have the transaction time, so you could artificially create that. You could basically bucket time into however many buckets you wanted and say any transactions within this bucket, I'm going to connect with edges based on time. So there's lots of ways to model time in the graph. What I just described is one, but yes, as other people are mentioning, there are methods like temporal graph networks that more explicitly consider time. That's more about time of when edges are added, or the dynamics on changing node features, for example. But there's lots of work and flexibility there, and it's also quite complicated. So, but I've seen it have great success in fraud detection problems. Something definitely to look into. Would it be a good idea to remove the feature that is highly connected to the target and test the model? Yes, those sorts of things are great for troubleshooting. And whenever there's these highly dominant features, it can hide lots of other problems that make it hard to discover. I think there's some systemic problem I haven't identified yet, because there's no reason the GNN shouldn't match the logistic regression. So extra credit to anyone that finds that. Cool. Any other questions or comments before we wrap up? Great. Well, if you think of anything, please join the Discord server, hang out there, and I'll be happy to ask any questions. And I'll let you know if I find the bug in this. But otherwise, I'll chop up this Zoom call into a video and put it on YouTube and send it out. Cool. Thanks, everybody. Have a great day.